I actually didn't have a lot of time to plan this session because last week I was kind of I kept myself busy with Durga Puja festivities, and even yesterday I didn't have a lot of time. So I apologize already if you think my thoughts are not organized enough or if it's messy. But I'll try my best to keep the flow proper. Um, so my plan for today is to first start by discussing some properties of what we call the Gaussian integers, and after that see a few applications. One application that we'll definitely see is the proof to the sum of two squares problem, which I'll just state right now. And if we have more time, we'll either discuss some other cool properties of the Gaussian integers or see some more problems. It really depends on how much time we have. Also, I'd really like if everyone is being interactive, because whenever I discuss some proofs, I'd actually like the audience um, to put in their thoughts so that it feels like everyone's working here. Um, and at the same time, I'd be glad if everybody could also keep their videos turned on so it feels more like a normal session. I'll start. So, yeah. Um, okay, so I think I'll probably try to keep a balance between not going too slow and not going too fast. So um, let me just start by just a second. Mm, yeah. So let me just start by first stating two theorems. The first theorem is what is commonly known as the Christmas theorem, and it's called the Christmas theorem because Fermat he sent a letter to some other guy, I don't remember the name, during Christmas, and there he mentioned this theorem. Um, it says that a prime a prime p, and I'm assuming everybody knows what a prime is. A prime p, it can be written as a sum of two integer squares. I think I should mention positive integer squares because zero doesn't count. As a sum of two positive integer squares, if and only if p is either equal to 2 or p is congruent to 1 modulo 4, right? We will discuss this. And the second theorem, I think Fermat also mentioned that theorem in that very particular letter, and that is, I think, known as the sum of two squares theorem, sum of two squares theorem. And I'm just using my own words here. It says that positive integer, positive integer n can be written as a sum of two a sum of two positive integer squares, a sum of two positive integer squares, if and only if the prime factorization. I think I'm messing the statement here. Yes. This is what happens. I think this is the first time I'm actually like doing something like this to a lot of people. So, in front of a lot of people, so I'm naturally a bit nervous. So let me see what the statement is. A positive integer n can be written as a sum of two positive integer squares, if and only if I'll just check the statement once. Why am I messing this up? Yeah, right. Sorry. If and only if primes of the form 4k plus 3, that is primes which are 3 modulo 4, primes of the form 4k plus 3 appear with even exponent in the prime factorization of n, right? In the prime factorization of n. So what this means is, this means really that when you write n as n in its prime factorized form, p1 a1, let's say, and pm am, then if pk is a prime which is 3 modulo 4, then the exponent, then ak, it has to be even. This is what the theorem says. So the first part of the theorem, the Christmas theorem, that is what was proved using the Gaussian integers, and the second part doesn't really require any Gaussian integers, just a little bit of number
Should
theory.
it be two positive integer squares?
Wait, I didn't write positive integer squares.
No,
Where exactly?
equal to 9.
Sorry, what? The set.
Should it be two integer squares instead of two positive integer squares? Because n equal to 9.
Oh, so you're saying is 0 counted as one of the squares?
Yeah, because your condition is satisfied by n equal to 3 square also.
Oh, yeah, right. Yeah,
Either
yeah,
n is a perfect
yeah,
square or the condition is
right, exactly. So the positive, it's not positive actually, it's just two integer. But it can be written as a sum of two integer squares. I'm gonna cut this here. Sum of two integer squares, yeah, right. That's not positive, I'm sorry about that. Yeah. So these are the two main theorems. I hope you understand the statement of this, right? And so now let's see. So first, let us deal with the first theorem, the Christmas theorem. Let P congruent to 3 modulo 4 be a prime. Okay. Then can we easily show that P cannot be written as a sum of two squares? Actually, it's pretty easy. If we write P is equal to a squared plus b squared, then can anyone see a very quick argument as to why this cannot be true?
A square is congruent to 0, comma 1 mod 4.
Yeah, exactly, that's correct. Because p is given to be 3 modulo 4, we're taking this mod 4, and p is 3, but a square can only be 0 or 1, so the only possible the remainders that you can get are 0 plus 0, which is 0, or you can get 0 plus 1, which is 1, or you can get 1 plus 0, which is 1 again, and you can get 1 plus 1, which is 2. So a sum of two squares can never be 3 modulo 4. So this is very easily not true. So if a prime is just 3 modulo 4, then it cannot be written as a sum of two squares, right? All right. So the only thing we need to prove is we just need to show that if P is congruent to 1 modulo 4, then we just have to show that uh, P can be written as a sum of two squares. Written as a sum of two squares. All right. So if we just look at this equation here, P is equal to a squared plus b squared, what we're trying to do is basically solve this equation. We're trying to solve this equation and find integer solutions for a and b, right? Well, this in itself is a little difficult to solve because we can't factorize them in the integers. For example, if we had, if we had equations of the form P is equal to a squared minus b squared, then this is a very easy equation to solve. We can just factorize it as P is equal to a minus b times a plus b. Then we check common factors. Check common factors. etc. And then we can analyze whether there are solutions for A and B, right? Similarly, if some of you are familiar with Pell's equation, a very simple type of equations, like one of the special cases of Pell's equations is a squared minus 2b squared is equal to 1. Definitely this cannot be factorized in the integers, but you can actually factorize it as a minus b root 2 times a plus b root 2 equal to 1, and then we are able to do a lot of things and finally get some solution by working with these type of factorizations. So naturally, what we can do is we can actually factorize p is equal to a squared plus b squared. We can't factorize it in the integers or or the reals for that matter, but we actually can factorize it if we are allowing the existence of numbers of the form numbers which whose square is minus 1, right? We can actually factorize this as a plus bi times a minus bi, right? Where I squared is equal to minus 1. Yeah. So this, I think this equation is really uh, what this equation is really what motivates the study of Gaussian integers, because a and b are integers, so you naturally want to uh, study numbers study numbers of the form a plus bi, where a comma b are integers, right? So I mean, this was just an introduction, just a motivation as to why even talk about Gaussian integers. But now I think we can get to the main thing. So Gaussian, I hope I'm pronouncing it correctly. Gaussian integers, right? um so so very simply, definition, uh the Gaussian integer is a complex number of the form a plus bi, where a comma b are integers, uh, where a comma b are integers. Yeah, basically that's it. And the set of all Gaussian integers it's denoted by this thing. It's noted by zi. Yeah. Uh, now I'm really not planning to go at all into any ring theory in this session, but for those who are familiar, zi forms a ring, and like a lot of properties would be very easy. You don't have to prove a lot of things, but we'll actually go through the proofs of some properties and do them by hand for the Gaussian integers here, because I'm not going to discuss rings at all. Right. So this is what the Gaussian integers are. They are complex numbers of the form a plus bi, where a and b belong to integers. A and bi integers, and the set of Gaussian integers is denoted by zi. Right. Um, all right. So very simply, if you just want to visualize what the Gaussian integers are, you just consider the Argand plane, the complex number plane, right? So that's why I'm using a gridded page here. This is the origin. This is the real axis. Like this. This is the real axis, and this is the imaginary axis. You have 1, 2, 3, etc. Here you have -1, -2, -3, and this is I, 2i, 3i, and this is what minus I, blah blah. 10 minus 3i, and all the points, all these points in the corners of the squares, they are all the Gaussian integers. So I'm not going to draw a lot of them, just going to fill it up sufficiently. Yeah, so these are really the Gaussian integers here, these points. Yes, right. Sorry for the bad drawing, but yep. Okay, so once, oh, okay, thank you. No, I usually draw better, that's why. So, all right, so this is what the definition of a Gaussian integer is, but just with the definition, we can't do much. We have to develop a theory, or at least since these are very much related to integers, we expect that some of the more common properties of integers would carry over to the Gaussian integers in some different form maybe. But so now the most basic property that we study in the beginning when we start doing number theory or working with integers is basically this Euclid's. No, is it Euclid or is it just the division lemma? I don't know the name. It's just, I think, the division lemma. I hope it's called the division lemma. That if you have integers a comma b, right, then you can write a uniquely in the form bq plus r, where q is an integer, so q and r both are integers. Where q and r both are integers, and r is one of these numbers, 0, 1, b minus 1. Yeah, is it Euclid's? Wait, I'm unable to see the chat.
Yeah, I think it's Euclid's division lemma.
Yeah, right. It's Euclid's division lemma. Yeah. So this is Euclid's division lemma. It's one of the basic properties of integers, and what we want to do is we want to have something similar for the Gaussian integers, right? So, but you see, the first problem that we encounter is over here. We are saying r is one of these numbers, right? So, in other words, we are saying that 0 is less than or equal to r, less than or equal to b minus 1. But for Gaussian integers, we don't have a notion of comparing two numbers like this. We don't know how to say whether 1 plus 2i is greater than 2 plus 1i. We can't compare to Gaussian integers, right? So the first question is, so what do we do? How do we first define? How do we first put a notion of size for any Gaussian integers? And I think the most obvious thing to do would be to take the absolute value, right? A plus. The most obvious thing to do would be to take the absolute value, a plus bi, which is the distance of this number from the origin, and this is just defined as root over a squared plus b squared, right? But actually, we are not going to take this. We're going to take a similar notion of size, and here's where comes our next most important definition: the norm, right? The norm of Gauss. I'm going to go to short forms now. With GI stand for Gaussian integers. The norm of a Gaussian integer a plus bi is n a plus bi is equal to a squared plus b squared. We just remove the square root from the absolute value, and the advantage we get is that, first of all, the norm is an integer, is actually a non-negative integer, right? It's a non-negative integer, and what else? Yeah, and the second thing is it's very similar to, and like it's already giving us a sense of how the Gaussian integers are going to be useful in the sum of two squares problem. Right, useful. I'm just going to write useful. I'm not write everything. We will see how using this definition is more useful than having the square root over it. Okay, cool. So some of the quick properties of the norms. Properties. Okay. So let alpha comma beta be Gaussian integers. Then we first, what do we have? Wait. Right. We first have n of alpha is equal to n of alpha bar, right? Where if alpha is a plus bi, then your alpha bar is a minus bi, and it's called the conjugate of alpha. Conjugate of alpha. Well, conjugates are useful because the product of the conjugates is actually the norm. So you actually have norm of alpha is equal to alpha times alpha bar. Yeah, should have norm of alpha is alpha times alpha bar. So they are very related numbers. In the complex plane, if this is your alpha, then your alpha bar, the conjugate is just going to be the reflection over the real axis. This is going to be your alpha bar. Right. And the second property is that the n functions, basically I'm talking about the function, is multiplicative. And I'm not going to show this, but it's just trivial to check by hand. You have n alpha times beta is equal to n alpha n beta, right? Yeah, that's cool. Okay, so that's all the properties you have for the norms. That the first, that the conjugate, the norm of the conjugate is the norm of the complex number is the norm of the conjugate, and the norm is multiplicative. All right, so now we'll first quickly put the norm to use. We will first show, I don't know what to write for this. Let's just let's just go with the normal one. Let's right. So which first we quickly check which alpha in Zi have a multiplicative inverse in Zi. Multiplicative inverse in Zi, and by that I mean a multiplicative inverse means if beta is a multiplicative inverse, if beta is multiplicative inverse of alpha, then you simply have alpha times beta is equal to 1, right? Oh, by the way, I hope it's clear that the integers form a subset of the Gaussian integers. Yeah, like the imaginary part is just 0. All right. So to see which numbers actually have inverses, we just take the norm of both the sides. Okay. So we have that norm of alpha times beta is equal to norm of 1, which is just 1 squared 1. And you have here norm of alpha times norm of beta is equal to 1. Now, your norm of alpha and norm of beta, they both are non-negative integers, right? I don't know the correct notation. They are both non-negative integers. Non-negative integers. Right? So it just follows that n alpha is equal to n beta is equal to 1. That's the only possibility, right? So if we write alpha as simply as a plus bi, then we have the norm of alpha is equal to a squared plus b squared is equal to 1, and you can easily see that the only pairs a comma b possible pairs are 0 plus minus 1 and plus minus 1 comma 0, which shows that the only possible values of alpha are plus minus 1 and plus minus I, right? So these are the these elements are the only ones in Zi which have a multiplicative inverse, and so they're given a special name. They're called the units, right? So these are the units. So the next definition is units are elements of Zi which have a multiplicative inverse and in Zi my handwriting is terrible. In Zi they are plus minus 1 and plus minus I, all right? And these are the analogs of plus minus 1 in your normal integers. You always know an integer up to the sign, all right? So once we're done with this, right, so we're done with the basic definition. So the next thing that we have to see is what divisibility means in the Gaussian integers, right? So if alpha comma beta belong to Zi, then we say alpha divides beta. Okay, this is the sign for divide. Alpha divides beta if there exists some gamma in Zi, right? Such that such that beta is equal to alpha times gamma. Yep. So if this is the case, the first thing that we can easily check is that if a comma b are integers, then a divides b in in integers, like the normal notion of division in integers, if and only if a divides b in Zi, and that is something that one can easily check, right? The second thing is if a is I am writing alpha. If a is an integer, right, and alpha is equal to a plus c plus di, actually c plus di is a Gaussian integer, then a divides alpha if and only if a divides both c and a divides d. All right. This one is also pretty self-evident. Yes. So this basically means that alpha divides beta in the Gaussian integers if using Euclid's division lemma, the remainder that you get is actually 0. All right. So I've talked about division, right? Yeah. All right. So another quick thing is that if alpha divides beta, then the norm of alpha divides the norm of beta. Yeah. Okay, these are all very trivial matters to check. Fine. All right. So, right. So with this in hand, we're actually going to go to the analog of Euclid's division algorithm for division lemma algorithm, whatever. Euclid's division. Let's first just do the Euclid's division lemma for Zi. All right. and the statement for the Gaussian integers is a little bit stronger than for the integers. So it says that if alpha comma beta belong to the Gaussian integers, then you can actually write beta is equal to alpha times some some gamma plus, let's say, plus r, right? Plus r, where gamma and r, okay, they look very similar. I'm not going to use gamma, I'm going to use w, right? Where gamma comma w, they belong to zi, and also, and the condition is that you'd expect that the norm of w is actually less than the norm of gamma, but what you get is actually stronger. That you can actually choose w, so that the norm of w is actually less than the norm of gamma divided by 2. This is the statement of Euclid's division lemma for zi, and actually this makes intuitive sense. I'll say why. uh, when we write, because when we're talking about division lemma for the integers, when a b belong to integers and we write b is equal to aq plus r, we're just taking r to be positive, right? So that's why we get r is less than, we get r is less than a, but 0 is less than or equal to r is less than a. But if instead of taking the absolute value, if r was allowed to be negative as well, right? So we restrict the range of r to actually what, minus a less than r less than a. So that means that we just say that the absolute value of r is less than a, uh, right? Then you see that in the number line, if you have, say, a multiple of aq, then no, wait, what am I saying? Right. Then if you chose r such that it could be either be positive or it could be negative, but it's actually going to be but you choose the one that's closer to a multiple of aq, right? Oh, sorry, that's closer to a multiple of a. Then definitely the absolute value of r is going to be a by 2, because you have a multiple of a here, some am, and there's some r here, r1 here, and there's some r2 here, right? And this should differ by and the difference between yeah, the distance between these is actually a. So the one that's closer to a multiple of a here is actually going to be, the distance from the multiple is actually going to be less than a over 2. Okay, so if you're just using absolute value, then this statement that we talked about for the integers, the Gaussian integers actually holds for integers as well, right? um, so let's just see a proof of this quickly, right? Proof of uh, division lemma for zi, right? So we have alpha comma beta belonging to zi. Okay, so we will just write alpha over beta. We'll see this quotient and we rationalize the denominator, and we get alpha times beta bar is equal to beta times beta bar, right? And to simplify matters, we write alpha beta bar as m plus ni. Okay, so what we get is alpha over beta is equal to m plus ni, and this is divided, and beta times beta bar is actually just norm of beta. Now now m n and norm of beta, they all are integers, so we can use our modified division lemma, where this remainder's absolute value just has to be less than the quotient divided by 2. So we write m as n beta times m1 plus r1, where, and we say that the absolute value of r1 is less than or equal to n beta by 2, right? And we similarly write n as n beta, norm of beta times n1 plus r2, and we say that absolute value of r2 is less than or equal to norm beta over 2. Okay, is this clear? I hope it's clear. Okay, so then if we go back to our alpha over beta, then this is just all right. So what are we getting? M is this. So we have n beta times m1 plus r1 plus I into norm of beta times n1 plus r2 divided by norm of beta. And okay, this is going to be m1 plus n1 times I plus r1 plus r2 times I divided by norm of beta. Okay, all right. So now the most obvious thing to do, we will just let gamma is equal to m1 plus n1I. Yeah, and so what we get is that alpha after, yeah, we'll just do a little algebra, and what we'll actually get is that alpha minus beta times gamma is equal to r1 plus r2I divided by beta bar, right? um, I hope this algebra was clear. This was clear, right? Okay, so now we just need to check that the norm of this thing here, because this is what we are hoping is the correct remainder, we just have to check the norm of this thing here is less than what do we want this to be less than? We just need to check that the norm is less than norm of beta over 2. So we take the norm. So we have norm of r1 plus r2I over beta bar, right?
Ritika, you're muted.
Oh, sorry, I didn't know. So where did I exactly stop speaking?
Well, starting the second line, so that's fine.
Okay, so what I just said is we want the norm of this thing. We just want to show that the norm of this thing is less than half norm of beta, and then we'd be home, because that's what we wanted to show, right? So we're just taking the norm of this thing here, and since norm is multiplicative, we can actually do this norm of r1 plus r2I divided by norm of beta bar. And the first one is just r1 squared plus r2 squared, and the second one is, and norm of beta bar is just norm of beta. We saw that before, right? And now we'll just use now we'll use the inequalities r1 less than or equal to n beta over 2, and r2 is less than or equal to n beta over 2. So what we get is that r1 squared plus r2 squared over norm of beta is actually less than or equal to, you can do this and you'll see it's actually less than or equal to norm of beta over 2. Yeah, so this proves this. So if we let this thing just be w, all right, so we get that alpha can be written as beta times gamma plus w, and the norm of w as desired is less than or equal to norm of beta over 2. And even if you uh, so at this point, I think it's good to actually see what the multiples of complex number of a Gaussian integer looks like in the eigenplane. What the multiples of Gaussian integer looks like, right? It's actually very satisfying. So I'm actually going to take some time and draw the thing nicely this time. All right. Okay. Mm-hmm. Let's just take the example of this one here. Let's just take this is, let's say this is alpha, and so we have alpha is equal to 2 plus I. Okay, alpha is equal to 2 plus I. So um, so I think we all know that. I think you are familiar with that. If you like, when you're adding two complex numbers in the Argand plane, it's just like vector addition. So if you have this complex, sorry, if you,
Ritika, you're muted.
okay, I have no idea why this is happening. I'm not even touching the laptop.
No, but I'm able to see an option to mute you. I don't see if this just seems to be some issue here.
Okay, okay, okay. Just let inform me when I'm muted again.
Yep.
Yeah, thanks. So yeah, I was just saying that in the complex plane, when you add two complex numbers, it's just like vector addition. So if you're adding this guy here with this guy, you're just going to take this and just, it's going to add them, and the the net result is going to be this complex number, right? um so the the thing to understand is that if you just look at the units, you have 1 minus 1, you have I and minus I, right? And if we can see, if we can visually see where, and I'll just mark them, this is 1, this is minus 1, this is minus I, and this is I, and these are the units. And if we can see where these units are actually going after multiplication, right? um, then any other number, alpha plus, then any other Gaussian integer a plus bi, you're actually write that as a times 1 plus b times I. So once you know where, once you know where 1 goes, so I'll just for example, um, 1 times alpha is just alpha. Why did I write it as minus 1? So this one, this is 1 and this is minus 1. So let's remove the excess points, right? So this is alpha, and 1 times alpha is just alpha, right? I'll check the chats later. Actually, I'm unable to see the chats right now. I just saw a notification, but I couldn't read the message. Um, right, what was I saying? Yeah. So you see that 1 times alpha is alpha. So 1, let's say 1, let's say just 1 is going here, right? And then you have minus 1 times alpha is my negative alpha, which, so minus 1 is actually going here, right? So minus 1 is actually coming here. And similarly, your if I actually am able to draw properly this time, okay, so this is what's happening. So I is going to this point under multiplication by alpha, and minus I is actually coming to this point here, right? Now, if I take any other a plus bi, I just have, it's, I know that it's a plus bi is a times 1 plus p times I. So when I do alpha times a plus bi, what I'm really doing is I'm doing alpha times a times 1 plus alpha times b times I. So first of all, let's say, let's just assume first a and b are both positive. So what I have here is the real component, this one is just first you're just stretching, 1 goes to alpha. So a times 1, you stretch the image of 1 by alpha. Let's say it's somewhere here. right? And then you take the image of I, right? You stretch image of I under multiplication by alpha, and you stretch that by b. Let's say b is something. Oops, wait, sorry. Yeah, so let's say b is something like this, right? And the net product, not the product, sorry, the net thing that you want is the sum of these two vectors after all, right? So I think I'm losing space here. Yeah, so what you will actually do is you actually translate this thing over here, and I hope this is correct, and this is the net result that you will get, right? So so any point that's after multiplication by a is actually going to be uh, something like walking along this direction, right? Like an integer many steps along this direction, where alpha, we just take alpha is like the length of the step. You take integer number of steps in this direction, followed by, sorry, the modulus of alpha is the length of the step, and then you go in this direction from this point anywhere over here or over here, and then you also walk integer many steps. So what you actually see is that the image of the all the points after multiplication by alpha is actually going to be something like a lattice, but it's going to be somewhat scaled and somewhat rotated. So if I were to actually draw all the multiples of 1 or 2 plus I here, then that would really look something like this. I have this here. So definitely 0 is going to be in the plane, right? So you're going to have this point, we are going to have this point, we're going to have all the points in this line, and again in the negative direction, right? We're also going to have these points, and similarly in the negative direction, and then we're going to have points like this, right? Because these are all the points that we can walk by our with our vectors and give in the given in the directions that we're allowed to walk. So this is somewhat what our what the multiples would look like. Not somewhat; these are exactly what the multiples would look like for our example here. I'll just draw a few more points just to waste some time. Um, okay, cool. Well, I hope this is enough. Um, yeah, cool. Right. These are really the multiples of 1 plus 2 plus I. Sorry, this is 2 plus I, and if you're multiplying, you get a whole new lattice of its own. And what your division lemma is saying, that you have a point here. Let's say this is some alpha, and your beta is 2 plus I. Let's say, then you can choose. Then you can actually choose any of these points, right? You can choose any of these points, and the distance. And the distance of these points from alpha is definitely and the complex number that you'll get, and the difference between these points and alpha will definitely have norm less than 2 plus I, but this guy here is actually going to have norm less than 2 plus I by 2, less than the norm of 2 plus I divided by 2, right? Simple Pythagorean theorem. So this is what the division lemma is actually saying, that you can actually do a lot better in the Euclidean in the complex plane, because you can go in any direction. There's no notion of positive direction or negative direction. Everything becomes equal, and it's the complex plane. So this was what the division theorem was. Right? I hope it makes some sense now. Um, Right. Let me just check what I was planning to do next. Yeah, definitely. So naturally, what follows is Euclid's division algorithm. Right. We have Euclid's, and I'm not going to prove this or anything. I'm just going to leave it to your intuition. I'm just going to tell you what this is because I already. This isn't something quite as interesting. Um. So. Hmm. Right. So the main use of Euclid's division algorithm is basically to find a greatest common divisor, right? So for uh, for Gaussian integers, we first have to define what a greatest common divisor is. So let's do a quick definition first. Greatest common divisor. I'm just going to refer here. The greatest common divisor of alpha comma beta in Zi is a common divisor. Is a common divisor, right? With maximal norm. With maximal norm. This means that if you take all possible divisors, common divisors of alpha and beta, and you then the greatest common divisor is basically a divisor with the maximum norm of all these. So we're saying so we can only so note that in Gaussian integers we can't talk about the greatest common divisor. We can only talk about a greatest common divisor because first of all, um, if d is if d is a greatest common divisor, is one greatest common divisor, then obviously minus d, I times d and minus I times d are also greatest common divisor. So basically you can multiply by units, and over here we can't just say take the positive divisor because there's no notion of a positive divisor here. So we can already see that there are four greatest common divisors. We'll soon see that these are the only possible greatest common divisors. There are just four possible greatest common divisors. So, but as of now, we just can't say the greatest common divisor, right? Okay, and so and division and Euclid's algorithm is as follows. You have algorithm is so you have alpha comma beta. None of them are equal to 0. Right? You first write alpha is equal to beta times gamma plus some, just be gamma 1 times some, let's say rho 1, right? Rho is the remainder, and the norm of rho 1 is strictly less than the norm of beta. Yeah, right? We do this, and then we take beta as our next alpha, and we divide by rho 1 this time. We say rho 1 times gamma 2 plus rho 2. All right, and we again do this with row 1. Now we take row 1 to be our new this thing, whatever it is, row 1, and we divide row 1 by row 2, row 2 times gamma 3 plus row 3, and we keep doing this all the way till till the remainder that we get is 0. We can't possibly we have always having um with 0, right? mm, right, just hold on. Is this what I'm saying true? Yeah, yeah, I am. It is true. So we go to some, say this is the penultimate step plus some row n plus 1, and we will finally, if we divide by row n plus 1 by row n, we divide row n by row n plus 1, and we get some row n plus 1 times gamma n plus 2, right? And we keep doing this until the remainder is 0, because if the remainder is non-zero, we if the remainder is non-zero, we again apply the algorithm. But since at every point you see the norm of the remainder is decreasing because this holds, so at this point you have norm of row 1 is less than norm of beta, and then you have norm of row 2 is less than norm of row 1, and this is a strict inequality, and this is going on. So at one point you're going to, and the norm is actually going to hit 0, at which point we know that the remainder becomes 0. So if we keep going till the remainder is 0, and in the penultimate step you have the last non-zero remainder, the claim is that this is a greatest common divisor of alpha comma beta. I'm not going to prove this. It's almost intuitively clear, but I'll leave that as for I'll leave this as an exercise. Basically, it's not even an exercise. It's yeah. All right. So the claim is that this thing is is one of the greatest common divisors of alpha and beta. So this is basically Euclid's division algorithm. It's absolutely similar to to your integer case, right? Um, so from this you again directly get the analog of Bezout's lemma for the Gaussian integers, that if d is a greatest common divisor of alpha and beta, then the equation alpha x plus beta y equal to d has a solution. X comma y. Again, your x comma y are Gaussian integers, but this can be solved, and the way you do that is simply run the algorithm backwards. You just run this. You start with this step, and then you go to this one, then you go to this one, and slowly you go to the go there. And this is something we are very familiar with from our integer case, right? And specifically what you get is, if alpha and beta are relatively prime, by relatively prime I mean the only common factors they have are the units. If alpha comma beta are relatively prime, right, then the equation alpha x plus beta y equal to 1 can be solved. Okay. Mm, all right. So yeah. So that's basically all about divisibility in Zi. And you have basic things like, if alpha divides beta and alpha divides gamma, then you know alpha divides some linear combination of beta and gamma, beta x plus gamma y for all sorts of x and y which are in Zi. Okay. This also follows almost tautologically. Um, right. Um, okay. Now, since we talked about GCD. Oh yeah. So another way to visualize GCD is, if you take if you have alpha comma beta, you plot the multiples of alpha and the multiples of beta in the complex plane, right? And then you actually take all the linear combinations of all the points that you get in the complex plane. All right. And that is also going to be some good looking lattice. And then the generator of that lattice, that is the smallest, the complex number, the complex number which actually generates, is basically the complex number of which all those points are multiples, is actually going to be the greatest common divisor of alpha comma beta. Okay. All right. I hope that wasn't a mouthful. What I mean is that then GCD is the generator for all. Okay, I'm not actually going to write this. This is fine. Never mind. So, right. So that's another way of thinking about the greatest common divisor. Um. All right. Okay. Now, let's just see one quick example. Not an example, sorry, it's just a property. If your alpha comma beta are relatively prime, okay, relatively prime. If alpha beta are relatively prime, and yeah, and we have alpha. Let's say we have alpha divides beta times gamma for some gamma belonging to Zi. Okay, then alpha divides gamma, right? And the proof is pretty simple. Since alpha gamma are relatively prime, we can write alpha x plus beta y is equal to 1 for some x comma y in yeah, for some x comma y in Zi, right? And then we multiply this by gamma. We multiply this equation by gamma, so we get alpha gamma x plus beta gamma y is equal to gamma, and your right. And now since alpha divides beta times gamma, we can write beta times gamma to be some alpha times q, right? So we have alpha gamma x plus alpha q y is equal to gamma, and since this side is divisible by alpha, so it follows that alpha divides gamma. This was as simple as that. Cool. So all right, now since we are done with divisibility, we are really coming to the crux of Zi, the most important property of Zi, which is actually going to get us home with our two squares problem, and that is the unique factor. Oh, before that, never mind. I'll just write it down. Unique factorization, right? Okay, but before that, I think I should say this: a prime. Um, a Gaussian integer p is a prime in Zi, right? If if its divisors are just our units or unit multiples of p. So just like the integer case, a prime p in Zi is defined to be a number such that its divisors are just either units or some unit multiples of p, right? All right. So the thing is not the so one would expect that the primes in integers should also be primes in Zi, but that's not true, because if you take, for example, 5 is a prime in Z, but it's not a Gaussian integer prime, not a Gaussian prime, and that is because you can write 5 as 2 plus I times 2 minus I, because you can factorize it, and these are all non-trivial factors, right? So 5 is not a Gaussian prime, all right? Now the next question is that then is 2 plus I a Gaussian prime? Is this a prime? Well, yes, it is a prime. And to see this, if we just write 2 plus I as alpha times beta, and we take the norm of both the sides, then what we have is norm of 2 plus I is equal to norm of alpha times norm of beta, and this thing here is just going to be 5. So you have 5 is equal to norm of alpha times norm of beta, right? But 5 is a prime, so one of them is going to be 1 and the other has to be 5. So we can just assume n alpha is 1, which means alpha is a unit. Alpha is a unit, right? So that means that if alpha is a unit, then 2 plus I is just some unit times 2 plus I. That's all it has to be. And so this is a prime, right? I think from this example, you can already see that if a plus bi is such that your norm of a plus bi is a prime in Z, norm of a plus bi is a prime in Z, then a plus bi is a Gaussian prime. This follows pretty obviously, although the converse is not true, right? I mean, just if the norm is a prime, then it's a Gaussian prime. But if it's a Gaussian prime, then the norm is not necessarily prime. For example, if you have 3. Now 3 is a prime in integers, but 3 is also a Gaussian prime, because if you write 3 is equal to alpha times beta, then the norm of 3 is 9, and you have n alpha times n beta. And if you assume that none of alpha and beta are trivial, none of alpha and beta are just units, right? Then none of these have norm 1. This is not equal to 1, and this is not equal to 1, which also means that this is not equal to 9. The only possibility is that norm alpha is equal to 3. So if you write alpha as some c plus di, then you have c squared plus d squared is equal to 3. But you can check by hand that 3 cannot be written as a sum of two squares in any possible way. So this is not possible, right? So we already start seeing something interesting here. We can already see that if a prime cannot be written, if a prime can't be written, I mean, a prime in integers, it can't be written as a sum of two squares, then it's already a prime. Then it has to be a prime in the Gaussian integers, right? And we know that, and we already saw very early on that if p is a prime in integers and it is 3 mod 4, right, then it cannot be written as a sum of two squares. Then it cannot be written as a sum of two squares, right? So all such p should be primes in the Gaussian integers as well. Yeah. Right. Yeah. All such p should be primes in Gaussian integers as well. Now let's just see one lemma about Gaussian integers first. If p is a Gaussian prime, yeah, Gaussian prime, and you have p divides alpha times beta, then either p divides alpha or p divides beta. And I'm not going to prove this. The proof is actually pretty routine. You just see if p doesn't divide alpha, then you show that p and alpha have to be relatively prime, and then from some previous lemma we know that we just did, we know that p divides beta. So this has to be true. All right. So using this, right, this has to be true. I think at this point, yeah. So at this point, I think I should just go to the unique factorization. Unique factorization. It says that any alpha in Zi can be uniquely factorized as a product of primes in Zi. Product of primes in Zi. This is just the analog of the fundamental theorem of arithmetic that we have in integers, that any integer can be, you have a canonical factorization. And what we mean by uniquely here is not just, is not that the factors are unique, because you can write f is equal to 2 plus I times 2 minus I, and at the same time you can write it as 1 minus 2I times 1 plus 2I, 1 plus 2I, right? So what do we mean by uniquely here is that, if you note, these this is actually just I times uh, I think it's minus I times 2 plus I, right? And this is your I times 2 plus I. So you see the factors are just your unit multiples. So what we mean by uniquely is that if n can be written as some pi 1 pi r is equal to pi 1 dash pi s dash, yes, then number one, we should have r equal to s, and after some suitable rearrangement, you should have pi k is equal to u times pi dash k, where u is a unit, right? So this is what we mean by unique factorization, can be uniquely factorized. So to prove unique factorization, there are just two steps. I'm not actually going to prove them. I'm going to give you the steps and a rough sketch. First, you have to show that there exists a factorization into primes, factorization, right, into primes, and the proof is by induction on the norm. All right. So the base case would be when norm of alpha is 2, because we don't have to care about units here. When the norm of alpha is 2, then you can check that alpha should be something plus minus 1 plus minus I, and you can check that this is actually just a prime itself. So it can be written as just itself, and then you induct um, yeah, and then you just break alpha into two non-trivial factors and take their norms, and that would be easy. And the second, you have to show the uniqueness, and this is also done by induction on the norm. Induction on the norm, and okay, and the lemma that we just did just previously, this one, let me just call this lemma what um, lemma star, right? So you just have induction on the norm and use lemma star, and you can show uniqueness. And how you would do that is, if you have pi 1 times pi r is equal to pi 1 dash times pi s dash, since the pi's and pi dashes are all primes, and you know that pi 1 divides pi 1 dash blah blah pi s dash, you can you'll get that pi 1 divides some of the pi dash primes, so you can assume that pi 1 divides pi 1 dash, right? And then you just remove you cancel out the pi's, and you'll be just left with units, and then you can just use the induction on the rest of the uh, products that you have, and this is going to actually prove unique factorization. All right. So with this done, we can actually now pretty easily do the sum do the proof to the sum of two squares problem, right? um, so we saw that, first of all, we saw that p equal to 2 is not a prime, is not a zi prime. Okay, we didn't see this, but it's easy because it's equal to 1 plus I times 1 minus I. All right. And we also saw that if P is congruent to 3 mod 4, then P is a Zi prime. Okay. Now, number 3, if alpha is such that your norm of alpha is an integer prime, right? Then alpha is a prime, is a Zi prime. Okay. Cool. Now, we are left with analyzing integer primes of the form 1 modulo 4. Okay. If we can show that P is not a Gaussian integer prime, then what do we get? Then we get that if P is not a Gaussian integer prime, then we can write P as some alpha beta, where alpha comma beta are not units, right? Because P is not a prime, so we actually have this good factorization. And then if we take the norm of both the sides, then we have norm of P, which is just P squared, is equal to norm of A times norm of B, right? And then it follows that this is equal to P and this is equal to P. Yeah. If you write alpha as A plus BI, then what this means is that A squared plus B squared is equal to P, right? And this shows that P can be written as a sum of two squares. As a sum of two squares. Yeah, I hope this much is clear. So this is all we want to show. We just want to show that P is not a Zi prime. P is not Zi prime. All right. So to do this, what the idea is that we will write P as a product of two Gaussian integers, and then we will show that P divides neither of the products, right? Which will show that P cannot be a Gaussian integer prime. All right. So more specifically, the idea is that we want to show that there exists some x, right? There exists some x in integers such that x squared plus 1 is congruent to 0 modulo P, right? Can we do this easily? I think in a previous session on number theory, you would have seen this proof. Right? So does anybody know how to show that such an x exists? Never mind. I'll just say it myself because of we don't have much time. So there are two methods actually. I mean, two methods that I know of. You can either take x to be not x. We just consider a primitive root modulo P. Right? We consider a primitive root modulo P. Okay, let's call it G. Okay. And since P, we can write P is equal to 4k plus 1. So we have G to the 4k is congruent to 1 modulo P, which means that G to the 2k whole squared is congruent to 1 mod P. Okay, but G is a primitive root, so the order of G is 4k. It's 4k, so it's not. So G to the 2k is not congruent to 1 mod P. Is not congruent to 1 mod P, right? So the only possibility is that G to the 2k is congruent to minus 1 mod P, which implies that G to the k whole squared is congruent to minus 1 mod P. So if x is taken to be G to the k, then you simply have G divides G to x squared plus 1. And the second very sweet method is by Wilson's theorem. So Wilson's theorem states that if you have some prime, if you have any prime p prime, then p minus 1 factorial is congruent to minus 1 mod p. Okay. So in our case, we write p is equal to 4k plus 1. So we have 4k factorial is congruent to minus 1 mod p. We write 4k factorial as, okay, so what do we write? 1 times 2 times all the way to 2k. All right. And then 2k plus 1 is actually congruent to, well, what is it congruent to? So, well, 2k plus 1 is just congruent to your p minus 2k plus 1. P is 4k plus 1. So it's actually, wait, my name is right. It's actually, I think, so what I mean is that you have 2k plus 1, which is congruent to 2k plus 1 minus p. It's actually equal to 2k plus 1 minus 4k minus 1, which is actually going to be negative 2k. And you can do that for all the other, all the upcoming factors. You have minus 2k times minus 2k minus 1 all the way to minus 2 times minus 1, right? And this is actually going to be congruent to 2k factorial times minus 1 to the 2k times 2k factorial, which is congruent to 2k factorial whole squared, and that's congruent to minus 1 mod p. So you could take x is equal to 2k factorial, and you see that p divides x squared plus 1. Right, so in any case, okay, there seems to be some. In any case, there exists x such that p divides x squared plus 1, and x is an integer, and you write it as x plus I times x minus I. All right. Now we also saw that if an integer divides, if p has to divide some x plus minus I, then p has to divide x and p has to divide 1, which is the coefficient of I. But this is obviously not true, right? This is obviously not true. So this is, so p is not a prime. P is not a zi prime, right? So p is not a zi prime, and because p divides the whole, p divides the product, but p doesn't divide any of these two individually. So p cannot be a zi prime, which actually means that p can be written as a sum of two integer squares. Two integer squares. Okay. And this actually proves the Christmas theorem. Right. This actually proves the Christmas theorem. So I hope it was clear till this, and I don't think we have much time. But the sum of two squares theorem, the whole theorem, I'll just let me see if I can just copy it. I'll just copy it, this one. This actually doesn't require any. So once you know that know which primes can be written as sums of squares, you don't actually need anything else, right? This can be proved simple by using simple number theory. And the key point to note is that if two numbers are sums of squares, a squared plus b squared, then their product is also a sum of squares, because of this very neat identity, ac minus bd whole squared. I hope I didn't mess that up, but you can check yourself. So because of this identity, so if you have any n, and let's say the p's, the p1 a1, you have blah blah, a2, and you have 2 to the something a, and then you have Q1 B1, QM BM, and let's say these are all primes which are 1 mod 4. Okay, and now 2 can be written as a sum of squares as 1 squared plus 1 squared. So 2 to the a can be written as a sum of squares because of this. Similarly, each of the pi's which are 1 mod 4 can be written as sums of 2 squares. So the whole thing can be written as a sum of 2 squares. All right, and now these are all 3 mod 4. Let's say these are all 3 mod 4. So, and the exponents are, let's say, 2k1 plus 1. This is 2km plus 1. All right, you write qk to the, not qk, let's say qi to ki plus 1 as qi. Okay, you don't have to write that. Actually, you can just now go for a very neat infinite descent, right? You say n is divisible by p, but it's not divisible by p. It has a prime factor p, which is 3 mod 4, but its exponent is odd. So you write it as, but it's a sum of squares, right? You write it as this. So is equal to pm, where your p is 3 mod 4, and the exponent of p is odd. Let's say it's 2k plus 1, right? So you have p divides a squared plus b squared, right? But which means that a squared plus b squared is congruent to 0 mod p, which means a squared is congruent to negative b squared mod p. And then you can just since it's a prime, and if we assume that b is not p doesn't divide b, then we can invert b, and then you would have ab inverse whole squared is congruent to minus 1 mod p, which actually cannot be true for a prime which is 3 mod 4. There cannot be an element x such that x square is minus 1 modulo p, because then you'd have, if we let this be x, then you'd have x to the 4 is congruent to 1 mod p. And you see that 4 is the order of x. Then you have that 4 is the order of x mod p. And uh, and since 4 is the order always divides p minus 1. So you'd actually have p congruent to 1 mod 4, which is not true, right? So even this can't be true. So the only possibility is that p divides b. I'm going to write only possibility is that p divides b, which implies p divides a, right? So you write n is equal to p c squared plus p d squared, and then you divide by p squared, right? Is equal to c squared plus d squared. Now, since the exponent of p was odd, right? So you are still left with an odd exponent of p here, because you just divided by p squared, and you keep doing this a lot, and you keep repeating this a lot of times till you are actually left with some p to the 2k is equal to e squared plus f squared, right? You do this a total of k times, and this one is actually going to have no uh, um, right. So what do we get? um, mm, so you'll just have the only one p in this factorization, right? um, you should have just one p in this factorization, because you're reducing the exponent every time, but it's always going to be odd. But then you'll again get that p divides e comma f, which would imply that p squared divides e squared plus f squared, which is not true. So that would give you your contradiction. So you can't have an odd exponent of p here, and that would prove the sum of two squares problem. Proves the sum of two squares problem. I kind of hurried over here, I think, because I saw that I'm already going taking a lot of time here. But I hope you get the idea. And even if my explanation was bad, it's a good thing to to try on your own, because it's a nice proof, but it's not too difficult to figure out on your own. Problem. All right. So since we're already out of time, I think this is a good point to stop. I I did have a few interesting problems that could be solved using Gaussian integers, and um, also modular arithmetic that can be done with Gaussian integers is another interesting thing. So what I'll do is I'll try to create I'll actually create a problem sheet, and also I'll try to put in some extra nice some other nice properties and ideas about Gaussian integers and problems, and I'll probably send it to the OMC organizers who could share it with everyone when the video is uploaded. So I guess this is a good point to stop here. Thank you very much for staying with me till the end, and even somebody who dropped by and went. Thanks a lot. Yeah.
Really sorry about that. Thanks a lot for coming.
Oh, no, no, it
I
was
mean,
my
did you say
pleasure.
you were not prepared? I mean, that was an amazing lecture.
Thank you. I personally thought I kind of messed up maybe the explanations, and if it was confusing, I'm really sorry about that. But I'll hopefully write clearer notes and share it with everyone. Yeah.